Welcome to this video on applying Gauss's law for a conducting surface and a sheet of charge. These are two different distributions of charge, but they're very similar, and so I'm putting them together so that we can get a better understanding by comparing and contrasting them. So the first thing we want to do here is always start with what's the big picture here? What are we trying to do? Well, we're employing a method and we're learning a method that will allow us to determine the electric field around some charge distribution, okay, where the charge is continuously distributed. And so what I have here is just a piece of the surface of something. So you could think that, I got a knife and box cutter and cut out a piece of the surface of a larger conductor. And so we're just focusing on this. Now, just to note, this is a perspective illustration or diagram, and this is the side version. And we're really going to be focusing on the side version here, but I will use a perspective version just to help you see it. So this piece over here is this little side piece that we can see. Okay, so we're going to employ Gauss's law, and if you haven't watched some of the videos leading up to this, you probably want to go back and check those out, otherwise this will be kind of confusing. The first thing we need to do is, when we're trying to figure out the electric field, we have to know where are we looking for the electric field. And so I'm going to say at this point right over here. Okay, so maybe from this shape, that point might be somewhere over here. Okay, and so what I want to do is set up Gauss's law, and the first thing to do is to choose an appropriate Gaussian surface. And remember that is an imaginary surface that will enclose the charge distribution. And it's not random. We pick the surface based on the fact that anywhere on that surface, or at least parts of that surface, the electric field will be constant. And so the way that I choose that is I'll trace a line of dots or maybe other points that are equivalent to the electric field at this point. So if you'd like to pause the video and try to do that on your own first, and then come back and I'll show you how to do it. Okay, so I'm going to trace the points. So any point that would really be equidistant from the side of this surface. So maybe over here it would look something like this. Okay, so anywhere along there I should have approximately the same surface. So what I'm going to do is I'm going to trace the line. Okay, and now the surface has to have or contain this line. And so if I look at it from this perspective, what I could do is I have to connect this line to some surface that will extend outwards through this shape. And you might think of it as, well, maybe I'll do a rectangular prism somewhat like this, right? And then obviously I need to draw the perspective in on this one, which is a huge test of my lack of artistic skill. So it's kind of like that. But what I'm going to do instead of a rectangular prism is actually just make a cylinder like this. And you can kind of think of that cylinder as projecting outwards, where this face right here is parallel to the face of the surface. And so over here on the side, what that might look like is, if I sketch out my Gaussian surface, it might look something like this. Okay, so we're seeing it just on the side, and so we can't see the round end cap on the side view, but just to help you realize that. The next thing we're going to do is we're going to draw in the electric field lines. Okay, now this is a positive charge, and so the field lines will point away from the positive. Okay, so I'm going to draw all these lines out like this, and it's a uniform charge distribution. It's important to note. Okay, so I'm going to draw all these electric field lines here. Okay, and the next step is to draw in the area vector for each side of the Gaussian surface. Now remember, the area vector always points normal to the surface. So for instance, if I had a circle, okay, in perspective here, the area vector would point straight up like this. So basically what I'd be saying is that's normal to the surface. So that's the way that the surface is pointing. So I'm going to go ahead and do that, and I'll do it for each surface. So this end cap surface, the area vector points this way, and these sides over here, you can imagine this being like a toilet roll, right? The sides would point basically kind of like this, okay? So over here in the side view, I would have the end cap, right? Like the round end over here, and then the side ends would point like this and like this, okay? Now I know this can be a little bit complicated because it's a conceptual surface that you're trying to draw on a two-dimensional shape, and it's a weird application. So keep practicing, keep trying to reason it, and then it will eventually start to click. So the next thing I need to decide is which surfaces have zero flux, which surfaces have maximum flux, or somewhere in between. So if we remember, electric flux is equal to surface integral E dot dA. So in other words, the dot product here, remember, is the cosine of the angle between the E and the A. So if I look at this over here, the angle between, just say, this electric field vector and this area vector is 0 degrees. But the area, or the angle between this area vector and this electric field line is 90 degrees. Okay, so hopefully you remember that the cosine of 90 degrees is 0. The cosine of 0 degrees is 1. So here there is flux, here there is no flux. So in other words, there is flux through the circular end cap over here, but there is no flux through the sides, okay? And then what we could say then is anywhere on the end caps we have the flux, but if I was adding to get the total flux of, this might represent the sides of, say, the toilet roll, those are 0. So really I'm only dealing with the end cap and not the sides. Now Gauss's law says that not only is the flux equal to E integral E dot dA, it's also equal to the amount of enclosed charge, the amount that's enclosed by the surface, divided by the vacuum permittivity. So we've enclosed X amount of charge on the surface of the object, okay? And so what I'm going to do then is write this amount of enclosed charge, because I'm not enclosing the entire shape, right? I've only enclosed a portion of it in the middle. And I did that very specifically because the sides here might have some, kind of weird effects that we'll talk about later, and we want to avoid those. So we've only enclosed some of the charge. And so a better way to write that, remember, would be to describe it in terms of the charge density and the area in this case, because I'm dealing with an area on the side. So it's going to look something like this. So what I'm going to do here is write integral E dot dA, and I'm going to go ahead and plug in sigma A for the enclosed charge over epsilon naught. Now I said that anywhere along the surface, right, this portion over here, the electric field is constant. So that's great. That's going to come out of the integral. So E integral dA, right, equals sigma A over epsilon naught. Now I kind of mentioned before that it doesn't matter what shape we picked here. It could have been a rectangular prism, it could have been a cylinder like we chose. The main point is that the area is just the end cap, right? The surface that is parallel to the surface of the shape. So over here, once I've summed up the area of the end cap, I just have the area of the end cap, and so that will be EA once the integration's done. You could put here pi r squared if you were, wanted to actually put the value of the end cap, but it doesn't really make that much of a difference, and I'll show you why in a minute. On the other side, we get sigma A over epsilon naught, and so clearly here the area actually cancels out, and I'm left with the expression E is equal to sigma over epsilon naught. And this, right, represents the electric field at some distance away from the sheet. Now, if you look at this, you see there's no variable that actually relates the distance away, right? So what we would say here is that the electric field is not dependent upon your distance away. So it's not dependent upon r in this case, right? It's only dependent upon the surface charge density and then the vacuum permittivity of the space. So in other words, if I have a more dense charge distribution, I'll have more electric field, which makes sense. So it's saying as you move if you move further out, it doesn't actually affect what's going on. And so this is for, at any surface, this is what's going to happen. Now let's get back to that idea about the edge effect. Now over here on this side and over here on this side, what's going to happen is the electric field's not going to be pointing in the same direction as it is here, right? So it's going to be something where it points upwards and outwards like this. And what we've seen is the Gaussian surface, or the flux, right? The flux is maximum when the surface that's chosen is parallel to the surface here. And so if we drew this a larger drawing, right, where we had, it kind of encapsulated the entire thing and the sides, we'd see that there would be some flux through the sides, and it may or may not be constant to the amount of electric flux over here. So when we're talking about this and we're looking at the electric field around a conducting surface, we're looking at it just at regions that are in small kind of cutouts of that surface, or if that surface is pretty large. But the main idea is that within regions pretty close is that there's no dependency upon where you place the position, because the electric field should be pretty much constant. If you think about it, it actually makes sense. If I draw a surface here, okay, and I picked a point right there, if this surface is really, really large, so I'll make it a little bit bigger here to exaggerate my point, no matter where you pick, right, you're getting contribution of the electric field in all directions, and so you really never get that much of a change until you move much further away relative to the size of the sheet. And so within small regions of the surface, we actually see this relationship. Now, a conducting sheet is very similar. The only difference is if it's a sheet of charge, right, the positive charge, maybe if we keep it the same charge distribution, so here we'll do a side view. Because it's just a thin sheet of charge, what's going to end up happening is I'm going to have electric fields on both sides of the sheet. And because of that, the Gaussian surface that I choose will be slightly different. So I could draw out all these electric field lines, and there'd be some coming off the back here as well. And when I draw my Gaussian surface, now remember the Gaussian surface is going to be drawn according to the point in question, so I'll pick that same point. I'm going to go ahead and draw my line of where the electric field would be all the same. Then I'm going to enclose the shape. Now this time I'm enclosing both sides, and the reason being is that this is a thin sheet where the charge is, and remember this is the side. It's really only one dimension thick, right? And then it has an area, so it doesn't really have volume. And so what's happening here is if I pick, maybe I'll do a cylinder again, something like this, right? I can still see that the end caps, there is an area vector on either of these that is at 0 degrees to the electric field lines. But on the top edges over here, and here, and here, and here, those have a 90-degree orientation between the field and the area, and so those don't count, right? They wouldn't have any flux, just these two end caps would. So if I set this up, what I'll end up seeing is that the electric flux is equal to integral E dot dA, right, equals to enclosed charge over area, over epsilon naught, apologize, and then we can write the Q enclosed again as sigma A, right? But here what we need to do is we have to make sure that what we're doing is when we add up this side, right? So E is constant, so I can pull that out. And remember, it's symmetrical, so this distance on this side and this side have to be the same. Okay, so I'll go ahead and write it over here. E integral dA is equal to sigma A over epsilon naught. And on this side, once I've summed up the area, it's going to be the area of one side plus the area of this side. So what I really end up having is 2EA equals sigma A over epsilon naught. So then clearly the A's again cancel, divide by 2, and I have that E is equal to sigma over 2 epsilon naught. And so it makes sense here that the amount of electric field on one side at that point over there is half sigma epsilon naught, because there is some over on the other side as well. It's distributed to both sides. But for a surface, right, a conducting surface, we know that the electric field only pans out on the outside surface, and the inside surface has zero electric field, and therefore zero electric flux, and therefore no contribution of field on the inside of the shape. So compare and contrast both of these, and you can see that what we have here is a very similar expression that also says it doesn't actually matter how far away you are from the surface. The electric field is somewhat constant until you get too far away for where the edges actually start to contribute to the electric field. So I know this is a pretty advanced idea, and it is, and the abstractness, if you will, is what makes this, I think, a little bit tricky. So go ahead and try to, absorb as much of this as you can, try to explain it to yourself, and hopefully it will start to click. In the next videos, we're going to take a look at different distributions that we haven't seen before.